This was our WITWAQ today, right? They said, is 10, 11, 12 in the column space? So is 10, 11, 12 in the span of the columns? That's an equivalent question of A, because that's what it means to be column space. And then because I know what it means to be span, right? Really what I'm asking is 10, 11, 12 a linear combination of the columns of A? But that's another, I mean, it's amazing how much of a foreign language this class is, right? There, linear combination, right? So really what I'm asking is, can we solve the following equation? 10, 11, 12 equal to, because what does it mean to be a linear combination? It means take C1 times the first column, right? Plus C2 times the second column, plus C3 times the third column, 3, 6, 9. Right? So you think about, when I asked this question, I pulled a chapter 3 vocab word out, which really kind of led to a couple of chapter 2 vocab words, but it's really a chapter 2 idea. Can you solve this equation, right? So anyways, do we have how many yeses, how many nos? What do you guys think? Give me a vote. Yes, we can?
I say yes too.
And I'm seeing some head shakes. No, we can't. How do we decide? Okay, those of you that say yes, how do you solve it? Or those of you... So yeah, we know that this is equivalent to forming... Really what this problem is asking me to do is to solve a system of equations, right? Well, okay. So maybe to solve this system, what's the easiest way to do it? Form the augmented matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then throw my 10, 11, and 12 here, right? So throw that in there. And then what? So maybe this is a way of doing it. Reduce row echelon form of that. Right? But I had some yeses and some nos, so it's very interesting. I guess we should just do that, huh? Or do you guys suggest something else? People that had their hands up, yes or no. Does anyone have other suggestions? Because there are other ways to tackle this. All right, well, because you know how to do the row operations, it's time to use some technology here. So A equals 1, 2, 3, 4, 5, 6, oops. 56.
56. With 1,
7, 8, 9.
4, then 56.
Yeah. And then my B is going to equal, well, 10, 11, 12. Oh, wait a minute. I'd really like to, well, there's a couple ways I could have done that, but I could have just pressed transpose. That would have taken care of it. But I did this. And now matrix M is going to be A with a B next to it. So I have the augmented matrix, and let me reduce row echelon form M. Whoa. So, interesting. Interesting. Let me try that again. There it is. So did we get an answer? Do we have solutions?
Oh, yes.
I guess we do, right? How do you know we have solutions?
We can get There's a free variable.
Yeah, actually, yeah. So there is a free variable, right? I mean, if we kind
The
of
free variable must be column 3.
write out what that says on the paper, I mean, I guess what happens is I have the reduced row echelon form would be 1, 0, was that a -1, right? Yep. And this is 0, 1, 2, and this is 0, 0, 0. I should know that as my favorite matrix. And then I have, so -9 1/3, right? So that's -28 thirds. And then I have 9 2/3. I guess that'd be 29 thirds. And then 0. So this is what I get, right? And so if I ask, what do I know about C1, C2, and C3? Well, I know from the first equation that C1 minus C3 is going to equal -28 thirds. I know from the second equation that C2 plus 2C3.
-28 over 3 at the top.
Yeah. And it's 29 over 3 is the second one. But C3 is a free variable.
And it looks like it's linearly dependent.
Yeah, so the columns of A are linearly dependent. That's true.
Well, I think if there's more than the trivial solution if the rank is less than m, it looks like. Is that
Yeah.
true?
Yeah, when you're talking about the 0 vector, then yeah. So I could say that C1 is equal to, well, since since C3 is T, I guess I could actually just bring it to the other side.
If the system is inconsistent, I guess there's no rank, it looks like.
So I should really zoom in a little bit.
I don't know if I said it the right way, but sorry.
That's okay. So here, try that again. We got C3 is equal to T, and so we can write C1 is equal to -28 thirds plus T. C2 is equal to 29 thirds minus 2T. And C3 is equal to, well, just T, we said.
I thought it was gonna be. I thought it was 0 for a minute, but
Yeah, so you could set it equal to 0, right? If you set T equal to 0, then one solution would be given by -28 thirds, 29 thirds, and 0. That's one solution. How many solutions are there, of course?
one. Oh, infinitely many.
Infinitely many, because you have a free variable, right? So this shows that, yeah, it is in the column space, right? There's actually infinitely many ways to write 10, 11, 12 as a linear combination of these things. One way to do it is take -28 thirds of the first column and 29 thirds of the second column. Okay, guys, so really, I guess the headline for my next note page is this. Does RREF of A tell us everything? Because I've had people say that to me in my linear algebra class. Oh, for any problem, just compute the reduced row echelon form and you know everything. Now, I don't know if that's true, but it's interesting because this theorem, right, all of these are equivalent, and part D says, hey, reduced row echelon form of A is the identity. And so on MATLAB, I have some examples for you. I have B as the matrix 1, 2, 3, 4. And if you reduce row echelon form that, you get the identity. Well, B is 1, 2, 3, 4, but A is my favorite matrix. And if I reduce row echelon form my favorite matrix, we know I don't get the identity, right? So these are somehow fundamentally different. Okay? So I guess the question is, what do these two scenarios tell you? So what did people come up with in terms of the theorem? Were there any of these that you know are automatically true if you know you get the identity? Go ahead, Jake.
The rank of A is n.
Rank of A is n, right? Let me write that down. How do you know that, Jake? How do you know the rank of A is equal to n?
I'm just
Yeah. Yeah, so like in our example on MATLAB, the rank of 1, 2, 3, 4, actually, MATLAB can compute that for you. The rank of B is 2. The number of non-zero rows is 2. Hey, by the way, I used to say that rank meant the number of non-zero rows, but I actually have a different definition now. Do you guys know the definition of the rank of A? It's the dimension of the row space of A. Yes, and it's actually equal to the dimension of the column space of A as well. That's a theorem that they prove in the book. That the dimension of the row space is the same as the dimension of the column space. But Stephen, I'm glad you said that, but of course Stephen used a vocab word. Let me make sure we all know what dimension means. Dimension is a linear algebra vocab word. I know, I'm being very deliberate, but I just think if I don't say it, how do you learn it, right? Do you guys know the definition of dimension? It is the number of vectors in a blank. In a blank of a subspace.
Matrix of a subspace?
In a basis of a subspace.
Basis.
Yeah, that word is basis. There's another word, basis. Again, I'm being very deliberate, but again, if I don't do it, who does, right? So what is a basis? You guys know what a subspace is, right? I don't have to do that one written. It has to contain 0 and be closed under addition and scalar multiplication. So we're good on that. But what about a basis? A basis is a set of vectors that spans the space and is linearly what? Yeah, thanks for being so unanimous with that one. Linearly independent.
Set of vectors.
That's a basis. Okay?
Vectors.
So there's a lot of vocabulary here that we need to know, I guess, if we really want to understand what this says. But I agree with what Jake said. Let's see if we can understand why. Why does the rank have to be n? Well, remember what we did when we first did the problem? The very first WITWAQ. I said, hey, take matrix A. And I asked you guys, hey, is a certain vector in the what? The column space. Is it a linear combination of the columns? And the answer was, yes, it is, right? It's in that span. But if I ask you what is the rank of A, the rank of A is only 2, right? So if I asked you guys, what is a basis for the column space, you would not use all 3 columns. That's right, you would just use the first 2, because when you do reduce row echelon form of A, you could see here we get a free variable. You don't need that 3rd column. You can represent anything just using the first 2 columns. And if you think about what you saw earlier today, remember, I even did let t equal 0. I didn't use the 3rd column. I didn't need to. It was extra. Does that make some sense to you guys? So I think that's all good discussion. Does reduce row echelon form tell me everything? Another thing that it tells you, I mean, they're all equivalent, so of course, but do you have a proof?
Yes.
What?
So since we have the row reduced, the RF of A, that's elementary matrices E
Yep.
n to E
Yep.
1 times A.
Yep.
So we can take the product of the elementary matrices, and that
Yep.
would be our inverse.
If reduced row echelon form of A is I, then A is invertible. Yeah, what your proof is with the elementary matrices works just fine. You know, another way to see it is this. How do you compute an inverse normally? Well, what you do is you take matrix A, and what do you put next to it, guys? The identity. And then you reduce row echelon form that thing. And what happens is, hopefully, in order to get A inverse over here, you need to get the identity. If you don't, you're stuck. It's not invertible. But if you do get the identity, it's invertible, right? And the proof relies on the elementary matrices argument that Nick was making and that the book shows as well.
I like
Okay.
that.
What's that?
I like that one.
Yeah.
Concise.
Well, yeah, it's kind of clear. So back up to the fact, hey guys, once you know that the rank of A is n, right? I agree. Jake says we have this theorem called the rank theorem. Let me write that down. The rank theorem says what? It says the rank of A plus the nullity of A equals n. That's what the rank theorem says. By the way, we know what rank is. Rank is the dimension of the row space. Do you guys know the definition of nullity? Has a similar definition. Nullity is the dimension of the null space of A, and you might say, okay, well, wait a minute. Do I know what the null space of A is? The null space of A is a set of vectors that you can take A and multiply by to get what? You're trying to get which vector when you go null space? The zero vector. We're trying to get the zero vector. Okay? So, let's do a quick exercise. Find a basis for the null space of A. Okay? Oh, I think we did that already. Didn't we do that one? With my favorite matrix? Let's do it again real quick, right? So what you do is you solve the equation A times X equals 0, right? How do you solve AX equals 0? Well, again, reduce row echelon form of A does it for you. Because we got 1, 0, negative 1, 0, 1, 2, 0, 0, 0, right? And then over here, you can imagine we have 0, 0, 0, because it's not going to change at all. And so if you think about what that says, well, it's kind of like before.
A free variable.
There's a free variable.
Infinitely many solutions.
Infinitely many solutions. Yeah. What do they look like? Well, I guess we know that C3 equals T, kind of like we had before.
Linearly dependent.
What about C2 and C1? I guess C1 also equals T, and C2 equals negative 2T, right? That's what we get. Who's with me? So if I said, find a basis for the null space of A, you could answer. How many vectors do I need, by the way? Well, I guess just one, because there's only one free variable. So you could say my answer is maybe 1, negative 2, 1, for instance. There's other answers. If you let t equal 1, that's what you get. So, what's the nullity of A? It's 1. What's the rank of A? 2. That adds up to 3. But here's an interesting question. What about matrix B? If I reduce row echelon form matrix
Nullity of
B,
Never mind.
I get the identity matrix, right? So what's the nullity of B? 0. What does that mean? It means there's no vectors in the basis? That's a strange situation. So here's an exercise I want to do very quickly. And actually, what I'd like you guys to do it, because this one you haven't done. Could you guys please find the null space of B where, you know, B is 1, 2, 3, 4. Okay? Try that for 30 seconds, and then we'll come back up and see what happens. Yeah, if I say find the null space of B, what does that mean? It means basically solve the equation Bx equals the 0 vector, right? So you could reduce row echelon form 1, 2, 3, 4 augmented with 0, 0. But if you did that, what would you get? You'd get the identity matrix next to 0, 0. And what does that mean? Well, if you're thinking of this as, you know, 1, 2, 3, 4 times, I'll call it x1 and x2 equal to 0, 0. What did we just learn when we did the reducer echelon form? Yeah, the first equation says x1 has to be, and the second equation says x2 has to be 0. So that's really weird. You don't have infinitely many solutions. You have how many? One solution. Now we knew we'd get one solution. We have a name for it, right? So this is an example where the only solution is the trivial one, right?
Wait, so that means it's linearly independent and the rank is equal to m.
Yeah, it means a lot of things. You're right.
That is true.
That is all true.
That the rank of m means only the trivial is equal to rank is equal to n means only the trivial solution.
Yeah,
right?
It's only the trivial solution to this equation. So yeah, this is why that rank theorem. Back up to what I was talking about before.
It's linearly independent. In case I forgot to mention.
Yeah. So all this stuff. I mean, it's funny because you hear Mike talking about these facts that he already knows, right? When Jake says F and G are basically equivalent, he's right. But once you know that the nullity is 0, then you know H, right? The column vectors are linearly independent. You also know the row vectors are linearly independent because the dimension of the row space, the dimension of the column space are the same. We also know it means the column vectors span Rn. Now you might say, why is that true? Well, I guess I need a little more work there. I need to maybe use the fact that it's invertible. Okay? But you could solve any equation and get a unique solution. That's what B says. And so if you get H and I, you get J for free. You have a basis. So that's where I wanted to go with this stuff today.